Welcome everybody. This is Smart Speaker Shenanigans, making the SONOS One sing its secrets. So first of all, small introduction. Last year I competed in a Pwn to Own contest. If you were here yesterday for the Soho talk by NCC Group, you know that in this competition there's various targets. And last year I went for 2 of the printers, and then I had some time left. And I decided to look at the smart speaker from SONOS as well. Turns out this target was quite a bit harder to get a foothold into. And I never managed to actually make an exploit in time for the competition. But this did lead to some interesting side research, and that's what we're going to be talking about today. So first of all, who am I? Independent security researcher from the Netherlands. Been with Hack in the Box for about 10 years. Mostly organizing CTF and giving various talks. I'm also sometimes active on the Twitters. You can find me on Blasty with a 4. So yeah, let's have a look. SONOS speaker is just a boring black box. I don't have one with me right now, but trust me, it's just a boring speaker. But if we open it up, we see a couple of things. Here we have a picture from the top and bottom of the PCB. In the upper right corner, you can see some small pins, which is the UART port, the serial port. So if we connect some wires there, we can get some output from the serial port. Below that is a mini PCI Express connector. This is normally where the Wi-Fi card goes. In this picture, the Wi-Fi card is actually being removed, so the slot is empty. Below that, we find the eMMC flash chip, typical BGA package chip, where the main firmware and the operating system for the SONOS resides. Then on the left in the middle, we can see the actual system on a chip, AMLogic A113D. And below that, we see some DDR4 DRAM. So just to give you a quick idea what goes on in these boxes, there's an Ethernet port as well. So you can connect it over Ethernet as well as Wi-Fi. So if we have a look at the serial port, well, in the past, there used to be a U-boot prompt that you could access, and you had some limited set of commands that you could issue, and some people figured out how to get code execution within this U-boot environment. But at some point, this was patched, so by the time I got my SONOS speaker, this no longer worked, which was a bit disappointing. But and then I looked a bit at the output from the serial port, and for one, I noticed that it says AXG secure boot. So I'm like, well, this is interesting. This thing apparently uses some kind of secure boot. But the goal was to find vulnerabilities in the SONOS firmware, right? So I thought if we take the flash chip, remove it from the PCB, and we dump it, we should be able to get our root file system. So that's what I did. I took a hot air station and I heated up the chip and gently removed it. If you look at the top in the middle there's a picture of the bottom of the chip. You can see the BGA ball array. If you pay some attention, you can see some balls are slightly dislodged, but overall it was okay. It was good enough to resolder this chip on an adapter, and that way I was able to get a dump from the flash. So I was like, great, now I have a dump from the flash, and we should be able to parse the root file system and get to the actual binaries. And now we can start vulnerability research, right? Oh, this one doesn't change. Okay. So it turns out that's not actually the case. A lot of the parts of the flash had a high entropy, and the parts that there were plain text contained, for example, an init ROMFS, so initial run disk image. And in there we find an init script, and then this init script will actually mount the root file system using encrypt setup LUX open. So it's a LUX encrypted volume. And so I was like, okay, well, that's great. They gave me all the key material. I can just mount the encrypted volume, and now I can see the root file system. So I tried just that. But when I did it and I looked at the first few bytes of the decrypted volume, it still looked like encrypted garbage. So I'm like, hey, what's going on here? And so we can use DM setup, -- show keys to get a list of all the device mapper entries and the keys that are being used for that. So this is after the key derivation function. So the thing at the top, the password that expands to that AES key eventually. But if we look at the AES key, we can notice something interesting, like the top 16 bytes are all FFF, which is kind of weird for a key, right? You expect it to be fully random or something like that. So something strange was going on there. So I decided to have a look at the Sonos website, and they offer various GPL downloads for GPL license code that they modified. And this is a treasure trove of information, contains patches to the Linux kernel and all that sort of things. And in there, I noticed that they modified the Lux subsystem to have some different way for deriving the actual key that's being used to mount the file system. And the way this is done is using a method called SONOS blob encrypt decrypt, and which in turn issues a vendor-specific secure monitor call to EL3 that gives back the actual key that is then used to mount the file system. So I was a bit stuck here. I didn't have code execution at the time on the Sonos. So I could not actually talk to the SMC, to EL3, and yeah, I got stuck. So I had a look around, and I found this amazing alarm clock from Lenovo. It's $50 at Media Market. And it turns out it uses a similar SoC to the one that's in the Sonos. So this uses the AMLogic A113X, whereas the Sonos uses the A113D. But I figured the part number is close enough, so it might be worth having a look. So I picked up one of those clocks, probed around the PCB for a bit, also found the serial port, and I noticed this one also uses secure boot, but is slightly less locked down than the Sonos is. So this is interesting. Maybe we can do some work on this target and then eventually port this to the Sonos, right? So the A113X and A113D is quad-core ARM64 CPU. Typical applications are for audio processing and yeah, so things like speakers, microphones, that sort of shit. There's Ethernet, USB 2.0, SDIO controller UART, all this fun stuff, right? And it supports Trust Zone. So there's this thing called the ARM Trusted Firmware, which is a reference implementation that you can find on GitHub, and it's used by vendors and OEMs when they want to implement some ARM platform that supports secure boot. So they can take this as a basis and maybe make some vendor-specific modifications to have like a good foundation for a secure boot chain, hopefully. So if we look at a bit more detail in how this ARM Trusted Firmware is structured, there's separation between the trusted world and the normal world. And when the device resets, the first thing that runs on the ARM64 cores is the boot ROM. And so that's a fixed piece of code that you can't easily get to. And then that will load the next stage bootloader, which will then in turn load the final payload that runs in the secure world called BL31. And it will also start a payload in the normal world called BL33. And this is typically a bootloader like U-boot or whatever, which will then chain load the Linux kernel and then eventually the userland, etc. So I managed to find a datasheet for this chip. It was not easy. There's this website where you can get data sheets by uploading other data sheets that are not yet on the website, and this way you farm credits, and using those credits you can buy other data sheets. And it's all in Chinese, and I had to sign up for a WeChat account, and it was a bit complicated, but in the end I got a data sheet. It has Xiaomi watermarks on it, but whatever. So from this data sheet I learned that the boot flow for this thing works by reading some GPIO straps to determine from where it's going to fetch the BL2 bootloader. So, and this can be either USB, SPI, eMMC, the NAND, or the SD. And if one of them fails, it's going to try the next one. And if the final one fails, it's just going to loop around till it hopefully eventually manages to boot a valid BL2 bootloader. So there's one interesting boot method, this USB thing, and uses a custom protocol. It turns out on the Lenovo clock, we can actually enter this USB recovery mode. This doesn't work on the Sonos, it has been disabled. But on the Lenovo this works. And I Googled around and I found an implementation called AMLboot, and it already talks to this protocol and allows you to send over a BL2 image over USB and then start it. So if we look at the commands for this USB protocol, there's a couple primitives that allow you to read and write and modify a certain region of the SRAM, so the tightly coupled RAM on the chip. And then you use that to upload the BL2 image. And then when you're done uploading all your chunks, you use the run in adder command and point it to the start of the image you uploaded. And that will start like the decryption and verification of this image if secure boot is enabled. And then when everything is okay, it jumps to this BL2 image. There's also some calls that allow you to poke some MMIO. It's restricted. I tried playing some tricks with it, but didn't really get anywhere. So one thing I noticed is if we take a valid BL2 image and we slightly corrupt it, and then we upload it over USB, and then we tell it to run it, it will decrypt it in place, and it will verify it, and the verification will fail, so it will not jump to the entry point. But the USB bootloader loop is still active, and you can still issue commands. So now if we issue the read command, we can get the decrypted contents for this BL2 blob, for which we do not have the key. So now we have a way for decrypting these blobs, which is interesting. So yeah, again, black box poking around this a bit to learn a bit more about the underlying cipher, because I had no idea. Turns out it's some kind of block cipher with a block size of 16 bytes, and it exhibits the properties of a CBC cipher used in CBC mode. So probably something like AES, right? So we can use this to decrypt BL2 images. Great. So next thing I noticed in the UART serial port output is that it parses this thing called the FIP table. And the FIP table basically holds a couple offsets and sizes for all the next stage bootloader blobs. So everything that's part of BL3X is addressed in this FIP table, and it loops over that, and it loads it. So using the decryption oracle, we can also decrypt this FIP table and all the BL3X blobs. So this is really useful. Now we can parse this table offline and extract all the blobs. So I took a portion of my NAND dump. I have a small Python utility that parses the FIP, extracts all the individual chunks, and so now we can actually start analyzing those in IDA Pro, Hydra, whatever. So great progress. So what our goal is, because we want to defeat this LUX volume decryption, we need data from the OTP and the eFuse array. We can normally access this, right? So we have to find a way to break into the secure monitor somehow. So if you follow this reference implementation from the ARM Trusted Firmware, we can see that vendors can extend the SMC dispatcher stuff with their own services. And in ATF speak, this is called SIP services. And vendors use this to add additional functionality that's not part of the traditional Trusted Firmware reference. So I figured this might be a good place to start reversing, because it's like closed source code and we don't have the source for it. So if we follow the ATF code, we can see that there's these service descriptor objects, and they point to the dispatcher for this SIP service. And conveniently it's called SIP SVC, and there's a name for this service as a string. So it's really easy to just find the handler for this vendor-specific stuff. Turns out there's 115 custom SMCs. That's like a shitload of code to be reversing, right? But a lot of them are like no-ops or like nulled out pointers. So it turns out it's only maybe around 40 or so. And then a lot of them are boilerplate to just return a pointer to a shared memory region that's used as some kind of mailbox interface. And then the remaining operations are cryptographic operations. And they give some limited access to OTP and eFuse. Of course, not to the full OTP and eFuse data. So the things we are interested in, like key material, is not exposed through the normal APIs. And then the remaining stuff covers something called secure storage. So secure storage is a way to have encrypted key value pairs using a key that is never exposed to the normal world. So the key lives and is generated in the secure world code, and the Linux OS cannot actually see this key, but Linux can ask to put items in the secure storage and retrieve items. So yeah, the secure storage lives in the shared memory, and it's not persisted in any way. So Linux or whatever, if it wants to persist it on flash, has to take care of that. So if we look at the actual commands that are relevant to the secure storage, we have a read command, a write command, just for reading and writing items. We have a list command for getting a list of all the items in the secure storage. We have a remove command for getting rid of an item. And then the most important command that you need to invoke at the very start is the parse command. So you shove an encrypted storage blob into the shared memory region, invoke the parser, and then the parser will internally populate and decrypt these values. So later they can be accessed using read and write. So yeah, the parser accepts one argument, which is the size of the blob, and then the actual blob goes in the shared memory region. The address for this region can be retrieved using another SMC call, but it's like a fixed address, so you don't have to retrieve it. And then the blob starts with a plain text header, and the header has a magic AML security, and then a couple more fields, and then there's a hash over the entire encrypted body, and then some padding. But yeah, by reading the code, I learned that if the key version field in this header is 0, then the hash is ignored. So for playing around, this is convenient. We don't have to reflect any changes we make in the hash. The other thing is there's this key mode field, which determines how the AES key and ASIV are initialized. And yeah, if we set this to 1, it's going to use a fixed 32-byte key from the data section of BL31. And since we have the decrypted BL31, we have this key, and IV is all zeros. Alternatively, if it's not 1, and on 0 there's an error, but if it's not 1, then it's going to take the CPU ID and concatenate the fixed value for both the key and the IV. But for all intents and purposes, it's probably easier for us if we want to parse blobs to use key mode 1, since it uses a fixed key. We have all these values. So, and then after the header blob, there's a parameter block, and that's decrypted, and it uses a TLV structure, so type length value, and it always starts with a header type, and then it's a nested TLV. So in there we find one subtype actually, which is called the encrypted size, and again holds the size for the rest of the body. And then following this parameter block is actually the encrypted storage entries. So what does a storage entry look like? Again, it's a nested TLV structure. They really like their TLVs. What could go wrong, right? And yeah, so there's a size for the name, there's data for the name, there's a size for the value, and there's the actual data for the value. There's a type of key, just an integer indicating what sort of item this is. A buffer status for indicating whether something has been changed. It's like a dirty flag. And then there's a hash over the data for the value. All right, so internally, after it decrypts these TLV structure, it will store all these keys in a fixed size array that can hold up to 64 entries. And these entries look a bit like what you see on the left. So it just reflects the values that were passed in the TLV in this fixed size structure. So the storage parser loop will loop over the encrypted body, and then we'll parse the TLV structures, and we'll compute the digest to see if it matches. And if everything is okay, it's gonna put this value in the keys array. And so it will keep doing this, and it's gonna increment a counter called key count. But there's a small problem because, like I said, there's only 64 entries that can go into this array, but they do not do any bounce checking on this index whatsoever. So you can go past the end of it. So it's like a typical buffer overflow. Not on the stacks, somewhere in the data section, which should be interesting, right? So yeah, initially I tried to use this overflow to go to the very end of the data section where there's a pointer to a function pointer table, for which the SMC dispatcher uses to get their function pointers. So I was thinking I can hijack the control flow by smashing my way all the way down turns out it requires a lot of keys and destroys quite a bit of data along the way, and some unfortunate alignment things over things we can't control. Fucks up this approach. So I studied the layout a bit more carefully, and I noticed that more or less right behind this global keys array, there's a scratch buffer for the parameter block. So the block after the header, right? And it's just a temporary scratch buffer. So if we look at the method that looks up the keys, we can see you give it a name, and it's going to iterate over the list, and it's going to use memcompare to see whether it finds a matching key, and if so, it's going to return the index for this key. But here it checks that the key index should not exceed the key count, but we can arbitrarily increase this key count, and it does not respect the original capacity of this keys array. So that's an interesting side effect that's useful for us. So again, if we look at the storage parser, we can see that if it fails to parse the parameter sector, then all 64 keys, so the original capacity of the key array, gets zeroed out. And then it will return from the function. But only after verifying the parameter sector, it will reset the key count. So this is useful. We can keep the key count at a number that exceeds the original capacity, and still remain this state. And so we can use this to forge key entry objects in this scratch buffer for the parameter block. So if we invoke the parser a second time, we can forge these objects by putting them inside the parameter block. And to prevent the key counter from being reset, we also introduce an error in the parameter block, so it bails out early and will clear the initial 64 keys, but our malicious forged keys live right behind it, so it's fine. This will stay. And the way we do this is we simply do not have the right format for the parameter block TLV. So again, in memory, key objects look like this. They have a name, nameland, etc. So what we do is we create one with an arbitrary name, hux, and we put a pointer in the value pointer field, pointing to anywhere we want. And we tell it that the size of the value is 8. And now, when we invoke the storage read and storage write commands, we get an arbitrary read64 primitive and an arbitrary write64 primitive, since in the forged object we control this pointer. So now we can read 64 bits of memory and write 64 bits of memory everywhere we want. And we can repeatedly invoke this exploit and chain a lot of these calls. So this is very useful. We can now finally hijack this platform pointer table. And this way we can redirect the control flow of the dispatcher. So I noticed that one of the custom SMCs in this dispatcher takes a couple of arguments that are just forwarded as is. So that's really useful, because if we hijack this entry in the function pointer table, we can get an arbitrary call primitive. So now it's kind of like a job thing, like jump-oriented programming, call-oriented programming, I guess, where we can call arbitrary functions with up to 3 arguments. So we use this to call back into a function that reads the eFuse data for us, and then we read it to some DRAM address, and from there we can retrieve it. So this is great. It allows us to read out all of the OTP data, and it hopefully has key material that we want for decrypting the LUX volumes. So next we have, while we have code execution in this privileged context, I figured it might be fun to have a stab at dumping the boot ROM for this device. Boot ROM contains code that we normally can't see, and would be interesting. Maybe there's some vulnerabilities in there, but if we want to analyze it, we'll have to dump it first, right? So from this borrowed datasheet, I learned that normally the physical address for the boot ROM is at FFFF0000. And it turns out that there's a minimal MMU setup in this EEL tree that I think they call it identity mapping, where the physical address matches the virtual address, but it didn't have the pages for the boot ROM mapped. So all we have to do is patch the page tables to reintroduce mappings for these boot ROM pages, and then we should be able to read them out. There's quite some details involved here about the ARM64 memory model. More of those details will be in the blog post that's released after the talk, but let's try to quickly gloss over it. So in EL3, the level 1 page table is specified in this special register, which can be accessed using MSR instruction, and it's called TTBR0 EL3. And another imported register is TCR EL3, and it contains some aspects of the translation unit. I'm not going to bore you with most of it, but if we decode the value that's in TCR EL3, we can see that they define a 32-bit address space with a 4K page size. So this means effectively that the level 1 page table only covers bits 30 and 31 of the virtual address. So 2 bits, that means we have 4 entries in this initial level 1 table. And so since we want to map FFFF0000, we need to follow the last entry in this table. And then we find the level 2 table address. And so in the level 2 table address, again, some bits from the virtual address, 9 in total, are used to index this table. And, so using some calculations on the back of a napkin, we can figure out that we need to go to entry 511, 1FF in hex, to find the address for the next table that covers this range FFE up till the end. So, and now we reach the final level table, and there's no more table indirection. So this is actually the page table entries themselves, and now we can start patching those. So if you look at some code, that's part of the exploit that will be released after the talk as well. You can see we read the level 2 table address, and then from that we get the level 3 table address, and then for the range of addresses that we want to map, we loop over this range and we patch page table entries into this table using our write64 primitive that we gained from the secure storage exploit. So using this method, I was finally able to dump the boot ROM. I tweeted a shahash for it back in November, and then promptly forget about this research until Hack in the Box was announced. So yeah, if you were to reproduce these steps, you'd get the same hash, hopefully. But now, this was all on the stupid Lenovo alarm clock, right? So how is this useful for the SONOS? Because we still cannot decrypt the root file system for the SONOS. So there's been some prior work on the SONOS speaker, and one interesting approach taken by multiple people, and it's been documented by Synactive, is to take out the Wi-Fi card from the PCI Express slot and put it in this specialized hardware that's compatible with PCI Leech, a tool by Ulf Frisk, that allows you to execute a DMA attack against the system over the PCI Express bus. So this can be used to peek and poke into all of DRAM. And it's a great way to get an initial foothold into the system. So what Synactive did is basically they patched the Linux kernel using this DMA peripheral, and they patch a string in the kernel called poweroff command. And poweroff command is literally a command that will be invoked in userland using a user mode helper at the time that this routine called orderly poweroff is invoked. Of course, this is typically not invoked, but then he also patches the VFS read routine, which is invoked all the time when any disk activity happens. And he hijacks a call to some function that's not that important to invoke orderly poweroff. So the end result is that periodically and quite often your custom command will get executed in userland. And he uses this to execute wget, and he execute a shell script. And that shell script will start telnetd. It will make /etc read writable, and it will update the passwd file to have a hash for a known password. So now we can telnet into the speaker and get a root shell. So the other problem is I didn't have the decrypted binaries for the SONOS BL31 payload, but turns out that the exploit for the layout in memory is mostly the same. So at least up till the read64 primitive, everything just works. So we can use this read64 primitive to dump the EL31 code or EL3 code from the SONOS, and now we can port all the offsets that are needed for the exploit. And to assist in doing this, I wrote a small kernel module, and it allows us to execute arbitrary SMCs, because typically you can do that. It's the kernel that issues these SMCs. We want to issue them from userland, and it also allows us to write to these various shared memory regions. And this is all exposed through debugfs, so it's really easy to interface with. So yeah, like I said, the read64 primitive works as is. So we can use this to dump the BL31 code, and then we adjust all the offsets accordingly. And now we have a working exploit for the SONOS. So I'm going to quickly, how does this play? This is autoplay. Let's see. All right, just a quick demonstration of how this looks. This is me SSHing to a Raspberry Pi. The DMA hardware thing is attached over USB. Looking at the ARP table, we see that SONOS is connected over Ethernet. We have a shell script that will patch the kernel using this DMA attack. So it's going to patch all these things. It's going to receive a connect back shell from the SONOS. Yeah, now we can like telnet into the thing. I'm going to log in. We start an HTTP server on the Raspberry Pi, so we can download our next stage payload. When we unpack this payload, and we load the custom kernel module, and now we can run the little exploit thing, and rerun it using the dump OTP. And there you have it. That's the OTP data for the SONOS that was well protected until now. The values in here are all specific to my SONOS speaker. So, I mean, you can make a photo, but it will not be too useful for your SONOS speaker. You have to do it again. And yeah, now it's going to dump the boot ROM. It's using the read64 primitive to read out individual quad words of the boot ROM. So there's a bit of a suspense. But, I mean, after all this hard work, right, who would mind a little suspense? So, it's going to go all the way up to 64 kilobytes, so we're halfway there, boys and girls and robots. Just hang in there a little longer. I know it's boring watching a counter. We still have plenty of time to kill, so it's fine. Yeah, and then so we get a copy of the boot ROM. I haven't spent too much time looking at the actual boot ROM yet. I mean, I've been meaning to, but so far I haven't found the time. Yeah, this is me realizing that BusyBox on the SONOS doesn't have SHA-256, so we have to use SHA-1. Sorry. If we run strings on the dump, we can actually see some readable strings in there. And yeah, so that's the boot ROM. Yay! Next, so we have the OTP data now. We can have a look at the OTP data, and by reversing BL31, I learned more about the actual structure of this OTP data and where all these values come from and what they're used for. For example, there's a digest over the RSA public key for secure boot. Then you have the AES-256 key that is actually used for decrypting the secure boot stages. So we were using this Oracle over USB, right? Now we no longer need the Oracle, because we have the actual key, and we can just do the AES-256 decryptions offline, which is nice. Then there's some more values that are used for enabling JTAG, but that's not actually too useful, because they burn some bits in the eFuse array that prevent us from actually accessing this. So that's like it's like a digest over a password that you would have to use to get into JTAG, but it's useless because JTAG has been completely disabled. And then, yeah, so that's all part of the future bits thingies there. And that also disables USB recovery on the Sonos, for example, and enforces a secure boot, that sort of thing. Then the green thing near the bottom is the AES GCM HW key. And this is the boy we've been looking for, because this is going to be relevant for actually decrypting the Lux volumes. And then there's some more things I don't quite understand. If someone figures it out, please let me know. At the very top, we have our CPU ID. So now we would actually be able to use the other key method as well, because it uses the CPU ID as a seed. Prior to this, we didn't have this value. So I guess it's nice to have. If Sonos is watching, please don't ban my CPU ID. I'm still planning to use this speaker. Okay, I will nicely put it back together, and yeah. So let's have a look at the volume decryption, right? So we got this key at the bottom in green, but we cannot directly use it. So on Sonos Flash, there's a couple pages that get provisioned during manufacturing called the MDP. The manufacturing data pages, and there's 3 of them actually, I think for legacy reasons, not entirely sure. And the structure of the MDP can be nicely decoded by following the GPL code that was released. Thanks to Alex from NCC Group for pointing this out after I painstakingly reversed most of it by hand. But cheers anyway. It's nice to have the real names for things rather than names that I made up. Yeah, and so we can find the encrypted rootfs and JFFS decryption keys in the MDP, in the final MDP blob. But so they are keys that are encrypted, and when those keys are decrypted, they will be used as decryption keys. So the encrypted keys are fed through this Sonos blob encrypt decrypt thing, right? And what this does is it invokes an SMC, and then code in BL3.2 in the L3 context will actually decrypt this blob. And to do that, it uses AES 256 in GCM mode. And the actual key that's being used, so the AES256 key, is a SHA-256 digest over the key that we got from the OTP. And then the IV for the AES GCM IV, you take the last 12 bytes of the blob, it's going to decrypt, and then you XOR that with either rootfs padded with 2 0 bytes or UBFS padded with 3 0 bytes. And the XOR key is rolling. So since we're XORing 12 bytes, that means you XOR with rootfs 00 root or UBFS 000 UBF. And so then the actual Lux key deobfuscation. So we got this funny key with the Fs at the start, right? And so here's a re-implementation of the entire thing. In Python, just so we don't have to follow pages and pages of C code. And it's going to look at the initial bytes to determine whether we're dealing with the rootfs key or JFFS key. And then, it's going to use the decrypted keys from the MDP3 and feed this into an HMAC using a seed with the value of Sonos space Lux, just an ASCII string. And then it's going to put the result of that HMAC into another HMAC. Like, I'm not a crypto expert. I'm not sure who came up with this, but that's how it works, right? And then finally, the result of this HMAC, the SHA-256 digest, is the final AES key that you're supposed to use for decrypting your partition. So how do we do this? We obtain this key. But we cannot directly feed it into Lux Open, because Lux Open uses a KDF and it has key slots and it's complicated. Maybe I did not understand the manual, but I didn't find a way to do this using a crypt setup. So I learned that the Lux images are aligned on a 2 megabyte boundary. And the actual encrypted data starts after this first 2 megabyte block. And so we can create a loopback device pointing to this actual encrypted body. And now we use our OTP dump, our MDP data dump, to get the actual decryption key. And then we invoke dm setup create in the correct way to use this key. So this is kind of what this looks like. At the top, we follow the approach from the init script. We pass this password thing, and we invoke lux open, and then we get this funny looking key that's prefixed with all Fs. We feed this into my little tool called SONOS tool, and we tell SONOS tool, well, here's my MDP3, here's my eFuse data, and I want the lux key for this obfuscated key, right? And it's going to do all these steps that we just explained, and then it's going to give me the final AES key. Then we use LO setup to loop back mount this image. We skip over the first 2 megabytes. Then we have a look at which loop device node is actually being used. It's loop 15 here. We have a look at how big this file actually is. Remove 2 megabytes from the start, divide by 512 because that's the default sector size. And then finally we have this monstrosity of a command line to tell the device mapper to mount this encrypted file system. And now when we have a look at the output from XXD on this device mapper mapped block device, we can actually see the magic for a squash FS file system. So after weeks of work, we can finally have a look on what's going on inside this thing. Pretty cool. So next up, Alex suggested that I should have a look at, well, no, he asked, did you have a look at decrypting over-the-air updates? And I was like, no, but I probably should, right? So the other week I looked into this. You can send HTTP GET request to this endpoint, and it contains a very big query string with all kinds of information that identifies your SONOS device, serial numbers, household ID, what have you. Model ID, major numbers, minor numbers. Turns out they don't really bother to check this serial, so you can use a bogus one if you just want to be a bit more anonymous. And then the response to this request is a custom binary manifest using this TLV-like structure. And so we decode this TLV-like nested TLV blob, and then we find the base URL that's used for retrieving the actual firmware. And from this base URL, we simply append the model and submodel number and some more shit. And then we can actually fetch this firmware image. Of course, these firmware images are encrypted. But with the powers that we have now, we should be able to decrypt them, right? So in the MDP3, there is a RSA private model key that is encrypted, that we can now decrypt because we re-implement this SONOS blob encrypt decrypt. And so we decrypt this key, and then that lets us decrypt some value at the start of the actual encrypted firmware data, which has an encrypted AES key. So it's crypto all the way down. And then eventually we get an AES 128 key that we can use in CBC mode with an IV that is all zeros to get the decrypted data. To be entirely honest, I don't know if the IV should be all zeros, but as it turns out, the first 16 bytes of the decrypted output are not actually used. So it works fine with an IV of all zeros, but I'm not entirely sure. But for our intents and purposes, it's good enough. So what does this look like? This SONOS tool that I made will be published on GitHub after the talk. We feed it our MDP3 data, we feed it our eFuse data, and we tell it download the latest firmware. And it's going to contact the SONOS servers. It's going to do the HTTP request. It's going to walk the binary manifest, and then it's going to save all the chunks to a folder on the disk. And then we can invoke SONOS tool a second time. And now we tell it, okay, decrypt this update for me. And it will find all the firmware chunks and decrypt them to a folder. And now if we have a look using a file, to look at the file magics, we can see there's a shell script. And again, Squash FS file system, but this time we got it from the OTA update. And some other blobs. One of them is a U-boot fit image, so that contains like U-boot, device trees, Linux kernel, that sort of thing. So yeah, what do we learn from this, right? If you want to enter pwn to own, it's probably not a good idea to spend a full month just decrypting the flash of your target, because you're going to lose a lot of time. But on the other hand, if you want to get a proper foothold into a system and you have the energy and motivation to maybe learn a new thing or two, it pays off to go a bit deeper. And now you can have a future-proof method of decrypting any SONOS updates or flash file system. Also, it allows us to inspect various stages of the boot process that were normally encrypted, and can now be analyzed for bugs. Like I said, I haven't really analyzed the boot ROM yet or any of the early BL2 stages from SONOS, but there should be plenty of interesting things in there. Another thing is I want to, well, maybe not me, but someone who is interested could add support for other SONOS products to SONOS too, and then we can extend this and make it a really nice general purpose utility for dealing with SONOS firmware. Yeah, some quick shout outs. My wife, who can now finally enjoy a SONOS speaker after I put it back together, of course. Peter Atkins for some nice chats. David Berhardt from Synactive for his work on the SONOS speaker and the PCI Express DMA attack. Alex from NCC Group for nerdsniping me into the OTA decryption. And yeah, let's see. Oh, yeah, we have a few more things. So if someone has a very powerful computer with maybe like GPUs or cloud GPUs or whatever, please crack this SHA-256 crypt hash for me, because it would allow us to, it's part of the password prompt that SONOS added to their U-boot bootloader. So you can still interrupt the bootloader by hitting some keys on the serial port, but it will ask you for password. So when I finally got the decrypted U-boot image, I was all excited because like, oh, now I can finally run strings on this thing or reverse a bit and find like the plain text password, right? It turns out that all I could find was the hash for the password. So they were a bit clever there. But if someone wants to have a stab at trying cracking this, be my guest and let me know if you find anything. Yeah, the final thing I wanted to say is SONOS. If you do like have this manufacturing provisioning process, you might want to carefully scrub your flash contents after provisioning, because if you look around in the NAND flash dump from this SONOS device, there's lots of leftover crap that's not actually in use anymore, and some of it relates to the initial provisioning of these devices, amongst which is a web key for, I guess, a Wi-Fi network that they use for internal provisioning. So if you happen to drive by their manufacturing plant and see a suspicious Wi-Fi network, try this key. But there might be other goodies in there. I haven't really looked, but it just seemed like something I had to point out because it's sloppy, right? Yeah. It's funny, this laptop updates slower than this. Huh? Okay. So write-ups will be published on my blog. It goes into a bit more detail. If this all went too fast for you, that's fine. There's lots of information to unpack. Maybe I skipped over some details and you want to learn more or read it in your own time quietly. So write-ups will be out soon. Tool and exploit code will be published on GitHub soon as well. The code is up. The repository is just marked as private right now. So I'm waiting for the talk to be over and then I'll unmark it so you can have a look. That's it for today. If there's any questions, I'll take them. Otherwise, feel free to catch up with me after the talk. And yeah, I hope you enjoy.
Thank you, Peter. That was really interesting, and yeah, it's clearly something that takes a lot of time to reverse engineer like this. Are there any questions from the room? Yep, we have one there.
Did I get it right that they cannot really patch it?
So in theory, this exploit that I use for BL3.1, they can patch it because that lives in code that sits in the flash. They could make an updated blob. But the problem is that by this time I already dumped all the key material. So whatever they do, I would still be able to decrypt any future updates and look for things. So yeah, once you have the keys, then yeah, it's kind of game over. Also this exploit, this bug that I used is a 0-day. Never bothered to report it to the vendor. I don't really do those things, I guess, unless there's like, financial motivation for me. So maybe someone wants to clue them in. Maybe they'll figure it out. I don't really know if they care. It's all part of the vendor reference code that Sonos copied, that Lenovo copied. And basically all the OEMs that use this chip, they copy this base code, right? So this issue might exist in many more devices, actually. I haven't looked, but yeah.
But you can also create your own updates, right?
No, as of yet. So there's signatures checking the integrity of the various bootloaders, and then even though we can re-encrypt the file system, there's also DM Verity set up. So I think it's hard, but this could be used probably like for some groundwork for a jailbreak type of thing. I haven't had time to look into it yet. Maybe someone will.
Thank you for your question.
Any more questions for the room? No? Okay, then I want to thank you for your brilliant talk.
All right, thanks for having me.
Okay.